Have you ever stopped to wonder how a computer, which is essentially just a really complex network of logic gates and wires, can actually learn to do something it wasn't explicitly programmed for? Think about it. We don't just sit down and type out billions of lines of code to teach a car to drive itself. That's impossible. Instead, we somehow drop the machine into this metaphorical learning journey where it just has to figure things out on its own. Welcome to This Explainer. I am absolutely thrilled to have you here today because our goal is to completely demystify exactly how machine learning algorithms are trained. We're going to break down the complex architecture of artificial intelligence into understandable, bite-sized pieces.
Okay, let's dive right into this. Here is our roadmap for today's explainer: unsupervised learning, semi-supervised learning, reinforcement learning, and dimensionality reduction. So, what actually separates these different approaches across the spectrum of supervision? Well, it all comes down to the volume and the type of signal or feedback provided to the learning system. This feedback is literally the absolute foundation for how we categorize these incredibly powerful algorithms.
Number 1. Unsupervised learning.
Imagine a scenario where a system gets zero feedback. It's a lot like a human trying to group exotic fruit on a table without knowing a single one of their names. In formal terms, this algorithm utilizes a data set comprising just inputs. Taught using completely unlabeled, unclassified, and uncategorized test data, the algorithms must identify similarities totally on their own and respond based on the presence or absence of those similarities in each new data set.
Now, what's really interesting here is that beyond just grouping things, a fundamental application is density estimation. So instead of just sorting data, the algorithm calculates the underlying probability density function. It's figuring out the structure, the distribution, and the likelihood of the raw data occurring in specific ways. When the algorithm assigns data into subsets, which we call clusters, we evaluated success using similarity metrics. We're contrasting two main things: internal compactness, which ensures high similarity between members of the very same cluster, versus separation, which measures how distinct and different those clusters are from one another. We want tight groupings, but with clear boundaries.
Number 2. Semi-supervised learning.
Moving along our spectrum, we find an approach that acts as the perfect intermediate bridge between human instruction and pure machine logic. Semi-supervised learning sits perfectly in the space between having zero labeled training data and having a completely labeled training data set. And this concept is brilliantly illustrated by the fact that when unlabeled data is combined with even just a tiny quantity of labeled data, there is a significant gain in learning accuracy. Why does this matter so much? Because in the real world, fully supervised training labels can be incredibly noisy, restricted, or just plain inaccurate, not to mention they're expensive to acquire. By adding just a few labels, this intermediate method saves money and effort, while creating much larger, highly effective training sets.
Number 3. Reinforcement learning.
Let's shift gears into action and reward environments. How do autonomous cars learn to drive? Or how does an AI learn to beat a grandmaster in a complex game? It's honestly a lot like teaching a dog with treats. The software agent operates in a given environment, taking actions with the sole goal of maximizing a certain concept of cumulative reward.
Now, the environment these agents operate in is generally represented mathematically as a Markov decision process, or MDP. This is basically a framework for mapping out states and actions. But the truly fascinating part here is that reinforcement learning techniques, many of which use dynamic programming, don't actually need prior knowledge of an exact mathematical model of the MDP to work. They are employed when exact models just aren't practical. The machine simply learns by doing. Because of this generic, adaptable nature, the versatility of reinforcement learning is staggering. Just listen to this list of fields it applies to: game theory, control theory and operations research, information theory, simulation-based optimization, multi-agent systems and swarm intelligence, and even statistics and genetic algorithms. It is an absolute multi-industry powerhouse.
Let's move to our fourth and final approach to see how this builds: dimensionality reduction.
As we collect these massive, overwhelming data sets, we desperately need data simplification techniques to make them manageable. Dimensionality reduction is the process of acquiring a set of major variables to reduce the number of random variables under consideration. Basically, it's lowering the size of the feature set. This mostly categorizes into either the extraction or deletion of features, simplifying the data so the machine doesn't get bogged down in all the noise. A very well-known technique here is Principal Component Analysis, or PCA. PCA beautifully transforms data from a high-dimensional space, like 3D data, down into a smaller space, like 2D data. This results in a decreased data dimension while still retaining the original variables in the model, and importantly, without altering the actual data. It relies on the theory that high-dimensional data actually resides along low-dimensional manifolds. Think of it like a 2D sheet of paper that's been crumpled up into a 3D ball. These algorithms help uncrumple it to find the simpler shape underneath.
So we've seen how machines learn through pure observation, tiny human hints, strict reward systems, and by cutting out the extra noise. It really makes you wonder, which type of learning signal do you rely on most in your own life? Are you an unsupervised learner, figuring it out on your own? Or do you need the clear reward signals of reinforcement? Keep exploring these ideas, and
We're unpacking a massive, fundamental debate right at the heart of artificial intelligence. I mean, you open up your newsfeed these days and boom, you're instantly bombarded with wild stories about the latest, greatest AI breaking boundaries, right? But underneath all those flashy headlines, there's an actual growing divide in how these incredible systems are built. And honestly, it's a debate that totally determines whether an AI actually works in the real world or if it just looks impressive in a fancy lab.
So we really have to ask ourselves here, what actually matters more in AI? Is it the model or the data? We're constantly hearing all this hype about super powerful algorithms, wildly complex neural networks, and just massive computing power. But is that really the true secret to AI success, or are we completely overlooking the raw material that actually fuels these digital brains? To really get this, we've got to look at how data scientists actually approach problem solving.
in artificial intelligence, there are basically two completely distinct schools of thought. On one side, you've got the data-driven approach. This strategy is laser-focused on enhancing data quality and data governance, all to boost the performance for a specific problem. Then, on the flip side, we have the model-driven approach. This method tries to crank up performance by developing completely new models and focusing on algorithmic manipulations, fancy software upgrades. Think of it like this. One focuses entirely on the fuel, and the other focuses entirely on the engine.
Now, in a perfect world, these two strategies would totally work hand in hand. You'd have pristine, perfectly governed data feeding directly into a highly advanced, flawlessly designed algorithm. Balancing both of these is the theoretical ideal to get the absolute best performance out of any AI system.
But let's be real for a second. That is definitely not what's happening. The reality is that model-driven techniques have sprinted way ahead. Everyone wants to build the next cutting-edge algorithm, which leaves the, less glamorous side of things severely lagging behind. Critical areas like data governance, data management, and data quality handling, they still have so much room for improvement. The tech industry has built incredibly fast engines, but we're seriously struggling to refine the fuel we put into them.
Section 1. The COVID-19 AI Stress Test. To really see this imbalance in action, we have a perfect real-world example from our source material. During the COVID-19 pandemic, artificial intelligence suddenly became absolutely essential. New projects sprang up everywhere overnight. People were using AI for recognizing the virus from CT scans and X-rays, estimating the entire course of the disease, and even projecting the overall number of fatalities. It was wild. AI was literally pushed to the absolute front line of medical science. And this was a massive, extensive global effort. And hey, on one hand, it absolutely increased our understanding of the illness, and in certain locations, it genuinely assisted clinical personnel working with vast populations. But when we compare this huge explosion of AI research to actual clinical implementation, there is a shocking catch that we really need to talk about. Very few. Despite the vast, almost unimaginable quantity of work produced during that emergency, only a very few of those projects were judged suitable for any actual implementation in the healthcare industry. Just think about that for a second. Thousands of advanced models were built, but almost none of them were actually usable in a real hospital setting to help real patients. So, the million-dollar question is why? Why did so many of these highly advanced AI models fail to reach hospitals when we literally needed them the most? Was the tech just not there yet? Were the algorithms too simple?
No, not at all. It wasn't because the algorithms were weak. The failure was primarily due to data quality difficulties. So many of these projects utilized duplicate photos just pulled from completely different sources. On top of that, the training data notoriously lacked external validation and vital demographic information. Because everyone was rushing the data collection phase, the actual foundations of these AI models were deeply flawed.
And because of those foundational flaws, the majority of these studies would completely fail a systematic review. They just failed to reveal their underlying data biases. So as a result, those incredibly high performance metrics they bragged about in their research papers, they simply could not be applied to real-world scenarios. I mean, an AI that scores 99% accuracy in a lab is totally useless if it learned to recognize a disease based on biased, duplicate, or unverified data, right?
Which brings us to arguably the most important rule in this entire field. Poor data will never result in superior performance, regardless of how strong your model is. It's an absolutely crucial feature of data science that we have to keep in mind. Bad data equals bad performance, period. There's just no way around it. You literally cannot outcompute poor data governance. Section 2. The ultimate data truth.
Look, if we actually want to move past the hype and deploy these systems in a way that helps people, we have to change our priorities. For society to truly reap the rewards of wonderful AI, real-world applications require an unwavering understanding of and commitment to 3 core steps for any data science project: systematic data collection, rigorous data management, and careful data consumption. Like we said earlier, the engine is only ever going to be as good as the fuel you give it.
Which leaves us with a critical question to think about the next time you're scrolling through tech headlines. As the industry races at breakneck speed to build the next groundbreaking AI, are we actually building smarter models, or are we just feeding them worse data? It's a vital distinction, and one for sure that will absolutely decide the true impact of AI on our society.
We're tackling a genuinely fascinating real-world scenario. Imagine a guy named Arjun. He's a newly joined instructor at a higher learning institution, and his big responsibility is to teach a comprehensive data analysis and model building course to a fresh batch of students. So today, we are going to walk through the exact teaching plan Arjun should use to show his class how modern businesses literally transform raw numbers into actionable, prudent strategy.
So let's just jump right in by asking the ultimate question. It's the one that every finance manager, operational executive, and of course, every single one of Arjun's new students will face. How exactly do we take a massive mountain of raw data and turn it into something that actually guides a business forward?
Well, here's our syllabus for today's masterclass. We'll cover the power of data, followed by the 4 levels of the analytics maturity staircase: descriptive, diagnostic, predictive, and prescriptive. Let's get started.
Section 1. The power of data, from raw numbers to prudent choices.
You know, Arjun's very first task as an instructor is to explain the true utility of analytics. And as David A.J. Axum points out, modern business is moving far away from gut intuition and basic spreadsheet reporting. Instead, it's totally transitioning into a predictive powerhouse that generates real, tangible business value through trustworthy, verifiable findings. Basically, analytics allows firms to gain deep visibility into their revenue, their costs, and ultimately, their profitability.
To truly wrap their heads around model building, Arjun's students have to understand these 4 distinct forms of data analytics. You can think of it like a staircase. Each step builds perfectly upon the last, taking a company from simply looking in the rearview mirror at the past to actively optimizing its future.
Moving up to Section 2, Descriptive Analytics. What happened?
Okay, so this is our baseline starting point. Descriptive analytics focuses exclusively on the past. It just uses basic mathematical tools, think arithmetic, averages, percentage changes, to aggregate raw data into a really easily digestible summary. It doesn't make any predictions at all, it simply sets the stage.
And honestly, we see this every single day in day-to-day operations. When you glance at an annual income report, or when a marketing team sits down to track Facebook likes, page visits, and response times to figure out user engagement, they're using descriptive analytics. The whole goal is just providing a historical overview of an organization's activities.
Now, in Arjun's lesson plan, he absolutely has to highlight the pros and cons of each method. The massive advantage of descriptive analytics is that it's just so easily applicable. You don't need any in-depth analytics expertise to use it. But the disadvantage, it only gives you surface-level insights. An annual report might look fantastic, but without any further analysis, you really can't use it to make future predictions.
That brings us to Section 3, Diagnostic Analytics. Why did it occur?
If descriptive analytics tells us our sales dropped last quarter, diagnostic analytics steps in to reveal the why. It involves a much more thorough examination of the data using techniques like discovery, drill down, and data mining. By identifying consistent connections and establishing actual causality, analysts can pinpoint the exact reasons behind a specific outcome.
Think about a real-world application here, like an HR department desperately trying to figure out why productivity is suddenly down. By setting up data models using Python or R, they can cross-reference quarterly performance levels against things like absenteeism and weekly overtime hours. And suddenly, these hidden correlations appear,
revealing the root causes of the trend. The real beauty here is that you derive deep value by asking highly relevant questions and solving specific problems. However, the downside is that it demands incredibly adaptable business intelligence platforms. On top of that, finding that true causality often requires integrating outside external data sources, which, let's be honest, can be incredibly complex.
Which leads us to Section 4, Predictive Analytics. What will happen?
Now we're getting to the really cool stuff. Predictive analytics utilizes probability, statistical modeling, and super sophisticated machine learning algorithms to anticipate future events. Instead of just analyzing past reports, these algorithms use current and historical data to make the best feasible assumptions about tomorrow. They're essentially filling in the missing pieces of the future.
Take RMIT University, for example. They actually partnered to develop clinical decision support software for aged care. By analyzing historical data, they can predict patient deterioration and, as a result, actively reduce emergency hospitalizations. And this exact same logic is widely used in e-commerce too, anticipating what a client is going to buy next based purely on their search histories.
The advantages here are massive. It enables proactive strategy, risk mitigation, and even fraud detection. But, and Arjun would strictly remind his class about this, there is a catch. Because it relies heavily on probability, it is absolutely never 100% precise. Plus, to get an accurate forecast, you're going to require enormous quantities of historical data.
Finally, Section 5, Prescriptive Analytics. What to do?
Prescriptive analytics goes a massive step further than just predicting the future. It's the absolute pinnacle of business intelligence because it actively recommends the best potential business actions. By utilizing rules, statistics, and advanced machine learning, it evaluates the consequences of different choices and then prescribes a strategy to capitalize on opportunities while minimizing hazards.
Think about a piece of technology we all interact with daily. GPS. A GPS doesn't just predict that there will be traffic. It calculates distances, road closures, and speed limits, and then prescribes the absolute ideal driving route to get you to your destination. Businesses use this exact same optimization logic for overall corporate performance.
While the advantage is definitely massive, minimizing human error and maximizing success is the dream, there is a steep trade-off. It requires highly specialized expertise and gigantic data volumes, which makes it pretty rare in simple daily operations. Plus, no algorithm can perfectly account for every single unpredictable external variable out in the real world.
And that brings us to Section 6, the analytics journey, completing the masterclass.
So bringing it all together, here is your ultimate masterclass cheat sheet. It shows exactly how raw data is sequentially transformed. We start with descriptive, reporting on sales. Then we move to diagnostic to find those HR correlations. After that, we jump to predictive to forecast e-commerce trends. And finally, we arrive at prescriptive to optimize our routes just like a GPS. This is exactly how a business turns raw data into a major competitive advantage.
I'll leave you with this final provocative thought to ponder, exactly as Arjun would with his new students. Where does your own team currently stand on this analytics journey? And more importantly, what specific data do you need to gather today so you can take that next step up the staircase and make more educated decisions tomorrow? Thanks for joining me.